Hey there and welcome back. If you're a physics student, chances are you've bumped into the legendary Irodov problem book. It's famous for really building that deep, intuitive understanding. Today, we're diving into one of its classics, problem 146. It's a fantastic little workout for our rotational kinematics muscles.
All right, so here's the full problem statement on your screen. We've got a solid body and its rotation, phi, is given by this function of time. Now what's our mission? Well, it's a two-parter. First, we need to find the average velocity and acceleration from the moment it starts until it comes to a complete stop. And second, we need to find the exact instantaneous acceleration at the very moment it stops.
But before we can jump in and start crunching numbers, we've got to make sure we're all speaking the same language, the language of rotation. So let's do a super quick review of the fundamental tools we're going to need from our physics toolkit.
First up, angular velocity, which we call omega. The easiest way to think about this is to compare it to regular linear motion. Just like linear velocity is how fast your position is changing, angular velocity is how fast your angle is changing. And this is where calculus comes in, right? It's the first derivative of our position function phi with respect to time. It's the language we use to talk about change.
And taking it one step further, we have angular acceleration, or beta. This tells us how the angular velocity itself is changing. Basically, it's asking, is the spin speeding up? Is it slowing down? What's the deal? Mathematically, it's just the derivative of angular velocity, which, if you think about it, also makes it the second derivative of our original position function.
Okay, our tools are sharp, we're ready to go. So, what's the game plan? You know, the entire problem really hangs on this one key event, the complete stop. That means our absolute first, most critical step is to figure out exactly when that happens.
We're starting with the equation they gave us for the angular position. To figure out anything about its motion, we need its velocity. So we've got to take the derivative of phi with respect to time. The derivative of at is super simple, just a. And for minus bt cubed, we just use the power rule. The 3 comes down, multiplies, and the power drops to 2. Boom, minus 3bt squared. And just like that, we have our equation for angular velocity at any time t.
Okay, let's hit pause for a second here. The problem uses this very specific phrase, complete stop. What does that actually mean in the language of our equations? What's the value of omega at that precise moment when the rotation just stops?
And that is the key, the light bulb moment. A complete stop means its speed, its angular velocity is 0. So we can take our fancy new velocity equation, omega of t equals a minus 3bt squared, and just set it equal to 0. This is what physics problem solving is all about, really, translating physical words into mathematical equations.
Now it's just algebra. Let's move things around. We get t squared equals a divided by 3b. We can plug in the numbers they gave us, 6 for a and 2 for b. That gives us t squared equals 6 over 6, which is just 1. Take the square root and bam, there it is. The body stops at exactly 1 second. That is a massive piece of the puzzle.
Awesome. So now we have our time frame. We're looking at everything that happens between time equals 0 and time equals 1 second. That means we're ready to jump into part A of the problem, finding those average values for velocity and acceleration.
Okay, for average velocity, remember the definition. It's just total displacement over total time. So first, let's find that displacement. We plug t equals 1 into our original phi equation. That gives us 6 times 1 minus 2 times 1 cubed, which is just 4 radians. And at t equals 0? Well, that's easy. Everything just goes to 0. So the total displacement is 4 radians. We divide that by our total time of 1 second, and we get an average angular velocity of 4.0 radians per second.
All right, 1 down, 1 to go for part A, average acceleration. Same idea, right? It's the total change in velocity divided by the total time. So let's look at our start and end points. At the very beginning, t equals 0, our velocity omega is just a, which is 6.0 rads per second. And at the end, at t equals 1 second, well, we already know that's when it stops, so the velocity is 0. So the math here is pretty simple. The change in velocity is always final minus initial. So that's 0 minus 6, which gives us, negative 6 rads per second. Divide that by our time interval of 1 second, and we get our answer, an average angular acceleration of negative 6.0 radians per second squared. But hold on, don't just brush past that negative sign. In physics, a sign is never just a sign, it's telling you a story. A negative acceleration here means the object is decelerating. It's slowing down. And does that make sense? Of course it does. We know the body is heading towards a complete stop. The math is confirming the physics.
All right, part A is in the bag. Now part B asks for something a little different. It's not asking for an average over time, it wants to know the instantaneous acceleration, like what's happening in that one specific snapshot in time when the body stops.
So, whenever you see that word instantaneous, your brain should immediately think one thing: derivative. We need a function for acceleration at any time. So we take our velocity function, omega of t equals a minus 3bt squared, and we take its derivative. The derivative of the constant a is just 0. The derivative of negative 3bt squared is negative 6bt. So our instantaneous acceleration is simply beta of t equals negative 6bt.
And the problem wants to know this value right at the stopping moment, which we already figured out is t equals 1 second. So all we have to do now is plug 1 into our brand new acceleration function. We substitute our values. We get beta equals negative 6 times 2 times 1, which gives us a final answer of negative 12.0 radians per second squared. Now notice something interesting here. That is double the average acceleration we found earlier. This is a perfect example of why it's so important to distinguish between an average over a whole trip and what's happening at one specific point.
So we did it. We crunched all the numbers, we got our answers. But, a good physics problem is about more than just getting the right number. It's about reinforcing the big ideas. So let's quickly summarize what we found and pull out the key lessons here.
Here are our final results, all in one place. We got an average angular velocity of 4.0 rads per second, an average angular acceleration of negative 6.0 rads per second squared, and a whopping instantaneous acceleration at the stop of negative 12.0 rads per second squared.
But really, the numbers aren't the most important part. It's the strategy. This problem is a great reminder of some core concepts. First, derivatives are your best friend for getting from position to velocity to acceleration. Second, you have to be a translator, turning physical words like stop into mathematical conditions like omega equals 0. Third, you've got to know the difference between an average value over a trip and an instantaneous value at one moment. And finally, never ever ignore the signs. They are telling you the physical story.
And I'll leave you with a little brain teaser to chew on. At t equals 1 second, the body's velocity is 0. It stopped. But it has this pretty hefty acceleration of negative 12. What on earth does that mean? It means it doesn't stay put. In the very next instant, that negative acceleration is going to grab it and start spinning it back in the opposite direction. It's one of the cool paradoxes of motion. Thanks for joining this explainer.